Hello and welcome to yet another video of my probability distribution mini-series. I have already made two videos about two different types of probability distribution. First, the discrete probability distribution, and second, the continuous probability distribution. In this video, I will continue my discussion on continuous probability distributions, and in fact, we are going to take a look at one of the most important continuous probability distribution in statistics, the normal distribution. Moreover, this video is a bit different from my regular problem-solving video, since I am not diving into the problem-solving right away. This is the lecture plus exercises type video, where in the first part I will give a lecture and explain some basic concepts about normal distribution, and in the second part there will be some problem-solving exercises. So let us start with normal distribution and standard normal distribution, probability density functions. So in order to make use of normal distribution, we must first learn what normal distribution is. And in many textbooks and online resources, including the Wikipedia article, the normal distribution is first introduced by its probability density function, which is this function, which gives this famous bell-shaped curve. And while this is indeed the strictest and most accurate definition of the normal distribution, introducing the normal distribution like this may sometimes fail to make students understand the importance of the normal distribution, thereby failing to motivate them to learn about the normal distribution in the first place. Therefore, I really want to start our discussion on normal distribution by briefly stating the importance of normal distributions. That is, normal distributions are commonly observed in many real-world phenomena. For example, if you measure quantities like height of the people, test score, weight of some sort of product, or the amount of annual rainfall, then there is a high chance that you will obtain a graph something like this. That is, you get the highest chance of occurrence at the middle of the possible values of our variable x, which is called the mean. And the farther the value of x is from the mean, the less chance of occurrence. Therefore, the number of occurrence of each possible value can be approximated by this curve, which is the famous bell-shaped curve of normal distribution. And the interesting thing is, even if certain phenomena do not necessarily obey the normal distribution, if we take enough samples and calculate the mean of sample values, that sample mean will follow the normal distribution. This is the famous central limit theorem, which I will mention again in the next video, where I will be talking about the sampling. Alright, so now we have understood that the normal distribution holds a special place in statistics. Let us finally take a look at the exact expression of its probability density function, which is also the bell-shaped curve. A normal distribution with mean mu and standard deviation sigma is denoted as n mu comma sigma squared, where this sigma squared is called the variance. Also, the random variable x following this normal distribution is denoted like this. The probability density function fx of the normal distribution is this, 1 over sigma times square root of 2 pi times e to the minus x minus mu squared over 2 sigma squared. Without translation and multiplied constants, it is essentially an e to the minus x squared kind of a function. The function is symmetric with respect to x equals mu, the mean, where the function has its maximum value. And with this equation of the probability density function, we can now discuss this figure on the Wikipedia page about the normal distribution. If you change the value of mu, the mean, then the maximum point, as well as the symmetric line of the graph, will shift. And if you change the value of standard deviation sigma, you will notice that the larger the value of sigma becomes, the more the graph becomes spread out. This makes sense since the standard deviation is essentially the parameter that tells us how much the data points are spread out from the mean, how much the data points deviate from the mean. Now there is a special kind of normal distribution called standard normal distribution. It is simply a normal distribution with mean 0 and standard deviation 1. Then what would be the probability density function for a standard normal distribution? Well, in this expression for the normal distribution, we can simply substitute mu equals 0 and sigma equals 1. Then we obtain this function, 1 over square root of 2 pi e to the minus x squared over 2. Since this is a special normal distribution, let us use phi x for its probability density function. So we can easily understand what standard normal distribution is, but the important and appropriate question is, what is so special about this standard normal distribution? Well, it is important because this distribution is used for the very important and useful process called standardization, which will be discussed as a separate part. Standard normal distribution, using standardization to calculate probabilities. Suppose that the random variable x follows the normal distribution n mu, sigma squared. This means that the expected value of x is mu and the variance of x is sigma squared, although I will not discuss the advanced integration in this video. Now, can we introduce a new random variable z in terms of x so that this new variable z follows the standard normal distribution? Yes, we can, and the relation is letting z as x minus mu over sigma. Now z following the standard normal distribution means that expected value of z equals 0 and the variance of z equals 1 squared. We can easily derive this using these properties, which I have discussed in my previous probability distribution video. So using these, we have expected value of z is given as expected value of x minus mu over sigma, which can be written as expected value of x minus mu over sigma by this property. And expected value of x is mu, so we have mu minus mu over sigma, so we have 0. And the variance of z is variance of x minus mu over sigma. And from here, we can write this as variance of x over sigma squared. So we have sigma squared over sigma squared, so we have 1. So there we have it. And finally, let us discuss perhaps the most useful properties regarding the calculation of probabilities. Suppose that a random variable x follows this normal distribution, and we want to calculate this specific probability, the probability where x is greater than or equal to a and less than or equal to b. This probability can be calculated by integrating the function fx from x equals a to b, where this fx is the probability density function of this normal distribution. Geometrically, this is equivalent to the area under the curve of function fx from x equals a to b. Now, since this inequality is equivalent to x minus mu over sigma is greater than or equal to a minus mu over sigma and less than or equal to b minus mu over sigma, and this x minus mu over sigma is z, from here, this probability is equal to probability of variable z having values from a minus mu over sigma to b minus mu over sigma, where z follows the standard normal distribution. In an integral form, it is equal to the integral of phi x from a minus mu over sigma to b minus mu over sigma, where this phi x is the probability density function of a standard normal distribution. And of course, the geometrical interpretation is that it is the area under the curve of phi x from a minus mu over sigma to b minus mu over sigma. We can directly prove this relation using simple u substitution, but I don't want to spend too much time on integral, so I will just move on. And since this standard normal distribution has specific constant values of mean and standard deviation, we can actually calculate the values of the probability of random variable z having values greater than or equal to 0 and less than or equal to small z for many different values of small z, which is this integral and also equivalent to this area, and create a table of these values called the standard normal distribution table, or sometimes standard normal table. Using this table, we can compute the probabilities related to the standard normal distribution easily. For example, what is the probability of z having values between 0 and 1.5? Directly from the table, we can see that this probability is 0.4332. Next, what is the probability of z having values greater than or equal to 0.5? Where graphically, it is the area of this region. And this area can be calculated by this entire area minus the area from x equals 0 to 0.5. So we can write something like this, and this area is 0.5 because it is the half of the entire area under the probability density function. Therefore, this probability is 0.5 minus probability of z having values between 0 and 0.5, and this probability is given as 0.1915 in the table, So we have 0.5 minus 0.1915. So we have 0.3085. Next, what is the probability of z having values between minus 1.5 and 1? Well, again, it is the area of this region, and we can divide it into two parts. The probability of z having values between minus 1.5 and 0 plus the probability of z having values from 0 to 1. Here, this probability, which is the area of this region, can be also written as probability of z from 0 to 1.5, which is the area of this region, due to the symmetry of the probability distribution function. Therefore, we have this plus this. So the first term is 0.4332, and the second term is 0.3413. So we have 0.7745. So what about random variable x following an arbitrary normal distribution? For example, suppose x is normally distributed by the normal distribution with mean 100 and variance 10 squared. What is the probability of x having values between 115 and 120? Well, if you try to use the probability distribution function of this specific normal distribution, then you have to compute the value of this integral. But instead of doing somewhat complicated integrals for every different probability density function, we simply standardize the variable by letting z as x minus mu over sigma, so in this case, x minus 100 over 10. Then this new variable z follows the standard normal distribution 0, 1 squared. Then this probability is equal to probability of random variable z defined as this, having values greater than or equal to 115 minus 100 over 10, and less than or equal to 120 minus 100 over 10. So we have probability of z having values between 1.5 and 2. And from the graph, it is this area. So using these two values, we can calculate it by this probability minus this probability, which is 0.4772 minus 0.4332, which is 0.0440. So this is how you standardize the random variable and calculate the probabilities. Now let us solve additional problems, the real-world application of normal distribution and standardization. Problem-solving exercises. So here's the first problem. Consider a catapult launching identical projectile every time. The distance to the point where projectile lands follows the normal distribution with the mean of 400 meters and the standard deviation of 15 meters. What percentage of the projectiles land at the distance between 415 meters and 445 meters? So we let x the distance to the landed projectile, then x follows the normal distribution 415 squared. And the value we have to calculate is probability of x greater than 415 and less than 445. Standardizing with z equals x minus 400 over 15, we have 415 minus 400 over 15, z 445 minus 400 over 15. So we have z greater than 1 and less than 3, which is this area. So using these values, we have 0.4987 minus 0.3413, which is 0.1574. So we can say approximately 15.74% of the projectiles land at the distance between 450 meters and 445 meters. And here's another example. A test score for the certain class follows the normal distribution with mean 65 and the standard deviation 16. You can say that the student who scored 89 points in this test is top X%. What is the value of this X? So this time let X be the score of the test, hence X follows the normal distribution 65, 16 squared. Then we calculate the probability of test score being 89 points or above. standardizing with z equals x minus 65 over 16, we have z greater than or equal to 89 minus 65 over 16. So we have z greater than or equal to 1.5, which is this area. So from here, 0.5 minus 0.4332, which gives 0.0668. Therefore, you can say that the student who scored 89 points is top 6.68%. Now there exist a whole lot of problems related to normal distribution and standardizing, but I think this is enough for a one video, so I will cover other normal distribution related problems someday in the future. I am planning one more video in this probability distribution mini-series, so if you are interested, please hit like and also subscribe to my channel, and as always, I will see you in another video.